Okay, so
good morning, everyone. So this morning, I'm glad to welcome Jonathan for this talk. You all see the title here. So please, Jonathan. So we have like a slot of 1 hour for including discussion, possible discussion. So it's up to you to manage the talk plus the discussion. So
great.
please.
Thanks for no, and thanks all of you for being here. So I'm going to try to talk about sub-mesoscale processes. So maybe some of you are not that familiar with that. So I'm going to try to explain a little bit more. Unfortunately, I won't talk a lot about machine learning, or I mean, I won't show yet groundbreaking results on the use of machine learning, but more explain how we are planning to use it, because we are still at early stages in this project and more or less this kind of work. Okay, so in briefly the outline, I'm just going to try to focus on sub-mesoscale processes, explain you what it is, briefly, why do we care about them, and focus on two typical examples, which are effects for the surface mixed layer of the ocean, and the bottom mixed layer of the ocean, and the different strategy we use currently to model these kind of things, and how we are trying to parameterize at least some impacts of these processes. And hopefully it should be not as long as not that long. We'll see. So let me know anyway when it's if it's too long. It's 11. Okay, so sub-mesoscales, very roughly, we are usually referring to sub-mesoscale currents in the ocean when we are talking about scales on the order of a kilometer. This is not the exact dynamical definition, but to give you an idea, we have currents in the ocean. So if you recognize, this is the North Atlantic in the background. And you see in colors the relative velocity, meaning that it's the curl of the velocity. So you get cyclonic regions when it's red, anticyclonic where it's blue. So you may recognize, I don't know if you can see my mouse, but my pointer. So you have the main current here, the Gulf Stream. You see big eddies. So that's the one we call mesoscale eddies, with typical scales of tens or 100 kilometers, or sometimes a bit more. And you have a lot of smaller scale things happening in many places in the form of small eddies, but most of the time in the form of fronts. So you see these lines of velocity, fronts, filaments, these kind of things. And these things are everywhere in the ocean when we can see with enough resolution, either with actual observations, satellite observations, in situ observations, or with models. Most of the time, so the dynamics of these sub-mesoscale currents is often strongly related to the presence of these fronts in the ocean. So when I'm talking about fronts, I mean horizontal gradients of the quantities, like temperature here, density, salinity. So here I'm showing you an image of a model for the Gulf Stream region again. So you see in colors, this is SST, so the sea surface temperature. So it is warmer in the southern part and colder in the north. So you see the Gulf Stream, which forms a very intense front here, a very strong gradient of temperature. You see the eddies with warm anomalies in the anticyclones called in the cyclones here. And if you look closely, you'll see that there are many frontal features in many places at smaller scales. So on all parts of the flow, even inside the eddies themselves, you see smaller scale structures. You see them even better if you look at, as previously, a field like velocity, because we are looking at the velocity gradient. So this highlights all these frontal features. So I'm showing you the same location, but now instead of SST, this is a relative velocity. So you see again the strong Gulf Stream. You see the mesoscale eddies with various sub-mesoscale or smaller scale things inside. And you see a strong sub-mesoscale soup, that's how it was called, with this eddies, fronts, and filaments, and all these kind of things here. And so this does not happen only in strong western boundary currents, which are very energetic regions of the ocean. But if you look elsewhere, so I'm showing you another example. So this time this is closer to the equator, the western equator Atlantic. So you see the Barbados, Brazil. You may even see there's a plume of the Amazon River around here. And you see, again, if you look at this field of surface relative velocity, how rich it is. So you see all type of scales of structures. You see things generated where the currents interact with the islands, for example. You see fronts also due to the presence of the freshwater plumes from the various rivers in this region. I don't know if you can see it with through the depending on if you have a good connection or not, but there's also a lot of flashing and modulation of the flow by internal waves in this case. Just to highlight the fact that this is, when you look at the scales, the sub-meso scales, you also see a strong impact of the internal waves. All of this will have interactions together. So this is a pretty complicated turbulent field with many time scales and space scales interacting together. So this, and this is again the surface. So this is where we have been studying sub-mesoscale currents for the longest, because that's where we can see them. And at least we have some satellite images, not necessarily satellite measurements of the currents at this scale, but we have at least images of the ocean colors, so showing us SST or the SST images and colors like chlorophylls, etc. So where we can see that we have a lot of these features. We know a lot less about what's happening below the surface, but at least from the models, we can see that there are also many things happening at these scales. So I'm coming back to the Gulf Stream as previously, except that now it's not at the surface anymore, but it is at 4,000 meters deep. And you may see again some kind of background motions related to the big mesoscale eddies or the meandering and interactions with this. So these white areas are in fact seamounts. That's what you see on the left. These big seamounts are the New England seamounts. So these ones are pretty big, but you have seamounts all over the ocean. And you can see that all this the large scale currents interacting with these topographic features here are generating these wakes, turbulent wakes everywhere. So with a bunch of instabilities happening in these wakes, creating so dissipation of energy, mixing of water mass properties. You see also formation of coherent structures in the form of these small sub-mesoscale anticyclones and small sub-mesoscale cyclones, which can then stay coherent and travel very long distances in the interior of the ocean. So when we put enough resolution, we start also to see that there's a very energetic environment, even at this strong depths. So now an important question probably is why do we care about these things? If these mesoscales are just wiggles, maybe we can just average them out and the result is the same. So, but it is not the case in for at least several of these impacts. So this is not a comprehensive list of everything related to sub-mesoscale, but a few things that I had in mind. So first thing, when you include this sub-mesoscale, so at least in models, you may change the fluxes of energy between the small scales and the large scales. So meaning that these small scales are not just a kind of dissipating energy of the larger scales. They may also be fluxing energy towards the larger scales. So you can have either a direct or an inverse cascade, downscale or upscale. So this makes these effects more complicated to take into account. So typically you have seasons, you have regions where the big mesoscale ZD will be stronger if you include some mesoscales in your simulation. They will have an impact also on mixing, especially at the bottom of the ocean. You can imagine just looking at again this vorticity picture on the upper right, how they create this strong heterogeneities. So with this fronts, so meaning that the temperature and other properties will be different from one place to the other, and this changes how the RC fluxes of each of the different tracers for the gases between the atmosphere and the ocean. So including all these heterogeneities has a net impact on how the ocean will interact with the atmosphere. And one important aspect of these submesoscale features is that they create strong vertical velocities. So in fact, in terms of amplitude, much stronger than the vertical velocities generated by the larger scales. You can see a glimpse of that by looking at the bottom right, where you have these two vertical sections. So just crossing through the simulation and showing you the vorticity and the vertical velocity below. And you see that locally the amplitude can be pretty large compared to the typical ocean values. Very localized and very large. And this also has an impact on fluxing heat, restratifying the ocean by fluxing density or tracers. And they are well-known effects, well-known but not necessarily completely understood nor parameterized yet, but known effects on how the biogeochemistry and the ecosystems will be impacted by this type of dynamics. So typically, this will help flux nutrients at some time and places inside the surface layer, and it can also change how the things will be going from the surface of the ocean to the interior. Like, for example, if you think about the carbon pump or this kind of thing. So there are a wide range of effects on that. Plus, of course, all these small-scale currents, they can generate a strong convergence zone, a strong divergence. So this would be important for plastics eventually, or all kinds of float samples, so all kinds of floating things at the ocean surface. So this has been shown recently by a few, especially one large-scale company in the Gulf of Mexico, where these structures have been highlighted with a much higher impact than what we suspected before. And as well, we had some previous work on that. Even in the deep oceans, the presence of these small-scale currents can also have an impact on how things will be dispersed and moved from one place to the other. Typically, larvae, hydrothermal effluents can be moved from one side to another. And how you include or not this type of motions can change a little bit this picture. So there are many effects. Probably one of the most, the one that has been studied for the longest would be the impact that these motions, these processes have on the depth of the mixed layer. If you from a recent article, I took this picture. So this is showing you the error in the mixed layer depth in the model. So the model is a typical ocean model that is used for climate simulation. So the typical resolution is 1/4 of a degree. That's what you will find in semi-6 type of models. So 1/4 of a degree at mid-latitudes, it's about more or less 30 kilometers, 40 kilometers. So obviously you don't get any of these submesoscale things, and you barely resolve the mesoscale as well, or at least just the upper part of it. And if you look at the mixed layer depth in this model, you see that there are places where, compared to observations, there are very large biases. So typically, it can be few hundreds of meters. So especially it's in high latitudes region, but also, for example, the Gulf Stream here and many places everywhere. And this is one of the effects we've been studying for the submesoscale and with the community in general. So we know for some time now that one important effect of the submesoscale processes, especially what is happening at the submesoscale fronts, is to restratify the upper mixed layer of the ocean. I won't get into the details of the processes. You see schematics with many of them, but you see a front and several processes, like, for example, all the frontogenesis drives a secondary circulation like this, but especially you have also instability like symmetric instability, mixed layer instability, a kind of bout-link instability inside the mixed layer, and these have an effect. So especially the mixed layer instability have a strong effect in converting potential energy to kinetic energy and restratifying the flow by doing this. If I show you a classical, one of the first papers showing these effects. So this is on the right, an idealized experiment. So the lines you see are isopycnals, so lines with the same density. And this is the upper 200 meters are well mixed, meaning that the density is homogeneous in the vertical. So this has been mixed by either heat fluxes at the surface or the wind or different things happening. And then you have at below 200 meters a strong stratification, meaning you have a strong variation of density in the vertical. And if you are able to resolve mixed layer instability, so these are unstable modes that will grow on this type of flow with a typical wavelength of a few kilometers. So the wavelength will depend on the depth of the mixed layer itself. So if you resolve them, you see this wiggles appearing. You also see that the initially vertical isopycnals are starting to bend like this. So meaning that you take some of the potential energy and convert it to kinetic energy. And if you wait enough, you'll start to see that you get a more, obviously, much strongly heterogeneous flow. And on average, you restratify the mixed layer like this. So the mixed layer depth, if you include this process, will be shallower for this type of flow. In terms of flux, usually we like to call it W prime B prime. So W is the vertical velocity, and B is the buoyancy, so related to density. So it means that the fluctuations are acting on average to, this is positive, so they act to restratify. So they have a net effect. It's not just a plus or minus that cancel each other. So this is for density, and you see also a net effect of these various processes for just the fluxes of heat, for example. So these figures come from a paper a couple of years ago, one of the first use of global submesoscale permitting simulation. So I'm going to come back to the simulation later, but typically a resolution of 48th of a degree. And they computed the effect of the submesoscales. So in this case, it was, I think, all scales below 50 kilometers, which is so pretty large definition for submesoscales, but still, point is you see the impact that of scales in generating a net heat flux. So you see at 40 meter depths in North Hemisphere winter or summer here. And typically you get values for the fluxes of heat up to 200 watts per meter squared, which are very significant values compared to the values you get from the surface forcings, for example. And in this case, if you look at even the mean temperature, if you include this type of dynamics or if you don't, so basically a coarser model which does not include submesoscales with a submesoscale permitting model, you see that you have a net impact on the temperature in the surface layer, which is up to half a degree in this case here. And so, so this is the example in the surface mixed layer, and briefly, I'm going to show you another example, probably less well studied yet, but which is also one of our focus here at Labs, is what happened at the bottom of the ocean. And basically, one of the problems is the same, is that with the typical climate ocean models, we do not resolve most of the processes happening there, and we get important biases. So showing this this picture, which was compiled by Clément using observations here, compilation of observations showing the vertical structure of the N2 is the stratification, so the green bicellular frequency. If you take a typical climatology from a model, I don't remember the exact resolution here, but typically it must be a quarter of a degree or maybe a bit less. You see big differences, especially in this region at the bottom. And if you compare the two together, you see that that's where large biases are located. And this is important because this the processes happening at the bottom are also have a huge impact for driving the overturning circulation in the ocean. So they have they can have large impacts on the much longer time scales and integrated properties of the ocean. And again, we have a zoo of instabilities and processes that can happen in bottom binary layers. In fact, most of the processes are kind of counterparts of what's happening in the surface mixed layer. So the people have been focusing on that only mostly over the last few years. And so we are kind of rediscovering that all the processes happening at the surface may also be at work at the bottom. So typically we have an equivalent of the mixed layer instability happening in the bottom mixed layer instead of the surface mixed layer. This is what I'm called BMLI in this case. And we have other kind of instabilities, symmetric instabilities, centrifugal instabilities. So without going into again the details of the dynamics, all these processes will be contributing one way or another to either increasing mixing, small scale mixing, so driving a path toward basically smaller scale turbulence and irreversible mixing. But they can also have the impact of helping exporting mixed water from the bottom layer. So in this case, increasing the water mass transformations and helping restratifying this bottom mixed layer, so with a global impact on this water masses densities in this at the bottom of the ocean. I also did a quick example. So this was from a simulation a few years ago where we were looking at typically resolutions of 100 or 200 meters to be able to resolve some of the processes happening in this binary layer. So you see a slope here in gray. You see a strong current flowing along the slope. So you basically generate strong negative PV, which is a trigger for this centrifugal instability type of things. The bottom layer in this case detaches from the flow and generates strong mixing and dissipation. And we think this kind of processes can be at work in many places of the ocean. Most of them are not sampled by observations and are not really modeled by our models, which in general do not have the good enough resolution to be able to resolve these processes. Only very recently, we started to have some observational proofs of that, or at least examples that this is really happening in places. This was from a big campaign, Dinopo, happening a few years ago, where they have been sampling this a strong abyssal current. You see a few thousands meter deep, with big importance because that's where this deep water are formed here close to Antarctica, and are exported through a few passes, including some where it flows along the topographic axis. And these very high resolution measurements, which are pretty difficult to obtain, are showing here. So in a nutshell, that you have strong instability happening, generating mixing, exporting waters, and an efficient way to change the water mass properties in these spots. And we have reasons to believe that it's happening in a wide range of areas. So can we are we able to resolve these processes? So surface processes, surface submesoscale processes, bottom submesoscale processes. So the answer is that it's pretty difficult for now to resolve these things with the current type of models we're using. So basically, you can see images on the right using data extracting from recent papers by Dong et al. Where they did some kind of stability analysis for the different type of instabilities. So in particular, mixed layer instabilities at the surface, bottom mixed layer instabilities, so at the bottom as the name states, and symmetric instability. So using like more or less realistic background flow, they look at the wavelength of the most unstable mode, which you can see is typically for MLI at the surface between 20 kilometers close to the equator and goes to 1-2 kilometers when you go to high latitudes. This will change also. So on the left, you see winter, on the right, you see summer. So depending on the season, you change the properties of the mixed layer. And then you change the typical scales of these processes. So this will become, the scales will be smaller in summer. If you look at bottom, what's happening in the bottom, you see that the color bar is not the same. So it varies between 100 meters to 10 kilometers for the wavelengths, but typically it's on the orders of 2 to 5 kilometers in most places. And symmetric instability at the surface is at even smaller scales. So we are typically talking about less than 1 kilometer and even less than 100 meters in most places. So if you look at this typical wavelength, you want to see if the model has a grid space which is fine enough to resolve that. So basically, you want to have a grid space which is at least a wavelength divided by 8 to give you an order of magnitude. So to be able to resolve these processes, so not everywhere, but at least on 90% of the surface of the ocean, you'd need something on the order of 1 kilometer for winter MLI, 500 meters for summer MLI. And you see at the bottom, it's more like 100 meters and maybe even less for 10 meters for symmetric instability. So we are not there yet, and we won't be there in the near future. If you think so, extracting from the same paper, like a prospective figure showing you so the grid spacing of models on the y-axis and the year time frame on the x-axis, and so you see the typical resolutions that have been used for climate type runs. So when I say climate, it's important because it means that it's runs that you need it's coupled runs, atmosphere, ocean, ice, that you must be able to run for many, many years, hundreds of years most of the time. So it's you are limited in terms of resolution for what you can do. And typically, actually we are at, you see 10, 20, 30. So the standards are basically 30 kilometers here for the current models that are used for climate studies. So we are far away from having the grid space necessary to resolve these processes at the surface, at the bottom, and even symmetric. So if you just extrapolate a kind of Moore's law, you see that it may take a very long time to be able to get there. And we know we don't have infinite resources, so probably we need to find other ways to take that into account into models. So in order to take that into account, we need to find a way to parameterize at least some of the impacts of these processes. So for example, a good example of that is what happens for the recertification of the surface mixed layer. So basically, we know that these submesoscale processes, in particular the mixed layer instabilities, have a mixed layer instability as a first order impact on the mixed layer depth. So based on idealized simulation, a few people have come up with scalings, so basically prescribing an overturning stream function in model. So if you have a front based on also the depth of the mixed layer, you have some here a coefficient which is based on idealized simulations. So this has been improved a little bit over the last few years, but basically the core of the parameterization is like this, and so you get a flux of Beyoncé that restratifies the flow as if you had MLI, which you can't resolve in typical models like this. And this has been shown to improve things. Typically, if you look again at the mixed layer depth error, so in the quarter of degree simulation here, when you include the parameterization, so this is how the error changes, meaning that in many places it is acting to compensate the error. So basically decreasing the depth of the mixed layer in most places by including this effect. So this is not perfect. So if you look this recent paper on that in 2020. So this is overcompensating in some places. This is not compensating enough in few of them. So there are still a lot of room to try to improve that. And people are also working on alternate methods to improve that based on other framework, energy scalings, basically something more consistent in terms of conservation. But this is something we've been able to do. However, it took a long time, took, I mean, almost maybe 10, 15 years to develop that based on theory, idealized experiment, testing, and it's still complicated to do. So that's where obviously using different type of machine learning methods seem to be a very promising way to, at least in parallel of this kind of only theory-based parameterization. And I think you've been talking a lot about this kind of topics in few recent OceaniX sessions. But basically, that was one of the main idea we had. So with a few colleagues at LOPS, basically try to build on these methods to try to find other ways to parameterize the effects. So of sub-mesoscale processes in the surface, or especially at the bottom where we really had nothing to existing, and we are still far from that. So the idea is very simple, and this is what we're trying to develop in a ANR project that started last year. Basically, from the coarse hydrographic U, V, T, and S variables of a model, we want to be able to predict what the sub-mesoscale, including other things, but most sub-mesoscale effects would be on momentum and temperature and salinity. So typically try to predict these eddy fluxes for momentum, or there are different ways, or trying to find an effective diffusivity and assume a certain form for the different terms. So this is clearly a completely ongoing work, and we haven't. We are just starting to think about how to implement that in our framework. But if we want to do that, we need data to be able to learn anything. Unfortunately, so especially at the bottom, we don't have much observations. So we have a few moorings here and there, but probably not enough to really do this kind of things, because even the moorings, it's pretty difficult to get eddy fluxes and the kind of things we're interested in. So we have to rely mostly on numerical models, realistic or idealized, different type of models, but mostly models. So what do we have as models to be able to quantify this effect of sub-mesoscales? So if you think about the state of the art in terms of global or basin mesoscale models, so there are a few of them which we call sub-mesoscale permitting. So typically with horizontal resolution in the range of 1-2 kilometers. So not yet able to resolve everything, but at least starting to get some effects of this, in particular at the surface processes, and some of the effects of the bottom, even if not necessarily the bottom mixture instability everywhere. So among these simulations, probably one you've heard of was a really groundbreaking simulation done by people at JPL, a global MIT GCM run at 48th of a degree, which was run for maybe a year or two in the end, something like this. You see a picture. This was the one that was used in some of the previous figures I've shown. So very, very impressive work on all aspects. There were also a few very, very good simulations done by people at in Grenoble, and I think I saw Julien there, Julien Le Sommer. So basically, with so even final resolution 60th of a degree here in the North Atlantic region. So that's where again you can start to resolve some of the processes happening at the surface and probably some others. Plus, I didn't talk really about this a lot, but there are also all the interactions with the internal ways that can also be tackled with this kind of models. And we have our in-house model as well. So we called it GigaTL, and which exists in various resolution. But typically the finest one, the most difficult to run, was a 1 kilometer run. So we have a slightly different grid, but basically we have more or less a slightly lower than 1 kilometer grid space everywhere in this domain here. And we've been trying, as all the two other simulations I've done previously, we've been trying to put all the realistic forcings we could in terms of tides, winds, river plumes, river forcings, all these kind of things. So this is our big simulations. Typically, we had a few challenges to solve over the past 2 years. Because the grids are very large, talking 10,000 points squared. And it takes a lot of processors, it takes a lot of computing time. And so far, we've been able to run a couple years for the highest resolution. So a couple years with tides, a couple years without tides, because we are using that to do sensitivity studies. And one of the easiest way to do sensitivity studies is just to cut things or not. That's one you can see with models, you cannot do with observations. And we have various longer runs with identical setup, just with a finer, coarser grid space at 3-6 kilometers. And we have other runs at even coarser resolution than that, but which are very easy to run compared to this one. And as you can imagine, if you want to study high frequency motions and small scales, it also requires a lot of storage. Currently, we have almost 6 petabytes of data, which are also a challenge to study. And that's basically what we are currently doing, that improving all the tools we had to really head up for dealing with this amount of data and being able to first quantify effects of sub-mesoscale things, and then use that to learn things and form parameterizations for the coarser resolution models. I think I'm getting pretty long, so I won't try maybe accelerate a little bit. All these models are, so this was preliminary comparisons of the different type of models with observations. I won't get into details here, but the idea is that the MIT run, NATL 60 run, COCO run, all these type of simulations, they are already doing a pretty decent job at stimulating the energy down to slightly high, I think, up to slightly high frequencies and pretty small scales. There are, of course, limits. You've seen previously that we only scratch the surface of the sub-mesoscale dynamics with this type of resolution. So that's why we need to go even further. So we cannot do that on a global scale, but we can do that on regional domains. So that's if you see one point here. So typically that's the kind of things we are doing on much smaller domains with typical horizontal resolution on the order of 100 meters. So again, we still don't resolve everything, but I mean, we will never really resolve everything. But we start to get a pretty decent job in the bottom layer as well. So this is what we are currently doing. So based on this Atlantic simulations, we have the tools now to nest things. And we can, so the nice thing is that we can get localized domains, but with as realistic forcings as we can, including remotely generating signals. and going to typically 300 or 100 meters domain. So these are things some of them we have already run, and some we are planning to run in the context of various projects. I'm not going to detail here. Maybe just show you quickly how it looks like when we can further increase the horizontal resolution and the vertical resolution, which is also something important. Here we are talking now about a small nest here with more than 300 levels in the vertical. It makes a big difference for many aspects. In particular, if you look at what's happening in the lee of a seamount in terms of the generation of waves, turbulent wakes, instabilities, mixing, and long story short, all these small scale processes, sub-mesoscale instabilities, and also lee waves in this case, are generating very strong mixing in the interior of the ocean that we are able to model here fairly well. I mean, we have no observations to compare with, so I'd say fairly well here. And another quick example that was done like last week, the nice thing is that it can be done in very short time frame now. Looking at what happens for seamount, but when you get closer to the equator, you see it's a very different regime. You see that the vertical scales are pretty different, and you get very intense mixing also in these regions that we are trying to understand now, quantify, and then hopefully try to learn in the different type of regimes to be able to use that in coarser models. Very briefly, so we haven't done much on learning the sub-mesoscale yet. We are just starting to train ourselves as well, to do that for mesoscale models, trying to learn the mesoscale for models that would be not mesoscale resolving. So we've been doing this kind of tests, trying to following a paper by Bolton and Zana, and a more recent paper by Zana, where basically they tried in an idealized gyre to learn the subgrid scale terms in the momentum equations. And this is the kind of thing we've been trying also as well. Degrade, coarsen the fields, get a coarse U and V, and based on that, predict the subgrid eddy momentum forcing. We've been testing that in realistic simulation in various type of dynamical regimes. At mesoscales, it works pretty well with this type of network. So this was a CNN here, a very simple one with you see convolution, deconvolution, and we are just working in 2D here, and so it's pretty straightforward to get this fluxes. And as in the paper of Bolton and Zana, it works pretty well in most regimes here. And so now there's a step to try to apply the same kind of things to the sub-mesoscale processes. So we'll start first with just looking at, we'll focus on mixing and recertification processes. But then we have a bunch of ideas also for other sub-mesoscale impacts that we want to tackle with this kind of. Now, once we have the data and the method, so there's a few projects either to look at bending storms, which would be like storms at the surface, but basically unusual strong velocity happening at the bottom of the ocean, which is important for a lot of other communities, thinking about people taking care of sediments or benthic geochemistry. Carbon exports, dispersion of larvae, dispersion of microplastics and flows. So there are a few projects that are starting on these aspects that we will be working on the next few months. So I'm going to stop here, and I think it was already pretty long. So thanks for your attention.
Thanks a lot, Jonathan, for this talk. That's the time for a discussion. Would anyone would like to start with the first question?
Yes, hello. I have a remark. It's not really a question. Hi, Jonathan. Thank you very much for this very nice presentation. I just wanted to say that I believe that climate models are often in 1 degree resolution in the ocean. The horizontal resolution is not 1/4 degree, it's usually 1 degree. So it would be even more difficult to parameterize, I imagine.
Yeah, no, yeah, thanks. Yeah, you're right. So 1/4 of a degree are already the best, some of the best ones. No, you're right. It's more 1 degree, but let's assume that in the next few years it will improve on this. So 1/4 of a degree. So probably there will be improvement in the next 10 years, something like this. But anyway, it will still be a very big leap to go from that to the sub scale stuff. But you're right, there's probably, and there's a lot of people working on that. Just parameterizing mesoscale in the climate models is already a very big topic. So I skipped that, but you're right, there's also a lot of work on that. And anyway, there's not like a clear threshold between scales. It's always a continuum. So we can just use the same kind of methods for different type of targets in terms of course models.
Okay, thank you.